Okay, in this video I'm going to go over some more graphs of quadratic functions. Now we modified our schedule a little bit this week, so I'm actually working through day 24 notes even though today is day 25. So if you'd like a copy of these notes, you can go into day 24, download a copy of the blank notes there and print them off in my classroom. Otherwise you can essentially copy these images that we're starting with here today. It's not real critical that you get your grid lines in place, but I think a good sketch would look something like this, where you have your X and Y axis, and then the fact that our parabola is sitting down here. In the video, I'll talk about the grid lines and the important data points on the grid lines, and then you can kind of replicate that on your notes. I would like to see the notes that you get through by following the video in today's class. So please make sure that you do take good notes and write down examples and send those back to me as an upload to day 25. So I'm going to cross this out and call this day 25 now. Okay, our objective in these first few problems is to identify the vertex form and the standard form of each function. And I think what I'll do is I'll just work down the left-hand column here. And if you'd like more practice and if you want to check your work with me later, you can work down the examples on the right side. Now before we begin, I just want to remind ourselves of the key data points for a quadratic function. There are 5 of them, and we started at -2 when x was equal to -2 and -1, 0, 1, and 2. We quickly computed the y values because our standard function was simply the x value squared. So when x is -2, y is going to be +4. When x is -1, y is +1, 0, 1, and 4. And again, we get each of these by simply squaring each of these numbers here. So if I square each of these, that's how I ended up with the y values on the right-hand side. Now I do this because this location here is our vertex. And if we can locate the vertex in our graph, and if we can consider the key data points for a standard shape graph, then we can interpret our a value for the function. Let me show you what I mean. In this example here, we have a vertex that's located at this position, and this coordinate happens to be 4, -4. So we have a vertex at 4, -4. Good. Now, we can determine our a value by looking carefully at this graph too. First off, I know that this graph is opening downward, so that tells me that my a value has to be negative. And also, I'd like to note that in a typical graph of a quadratic, from this origin, we would step to the right 1 unit and down 1 unit. From that origin, we would step to the right 2 units and down 4 units. But it doesn't look like our graph is striking either of those key data points. It's actually down a little bit further than that. So from this origin, or from this vertex, if we step to the right 1 unit, we actually have to go down 2 units. And that's twice as tall as normal. If we step to the right 2 units from our vertex, from the new origin, if you will, we actually have to drop down 1, 2, 3, 4, 5, 6, 7, and 8 units. And that's actually twice as tall as normal. So because this graph is basically twice as tall, or I guess you can casually call it twice as steep, I'm going to say that my a value is -2. So with that in mind, we can now write our vertex form of the equation. This is really easy. The vertex form is simply y equals, or f of x. Let's get practice with our function notations. We'll say f of x is equal to -2 times x minus 4 squared minus 4. And we know that this is the format because in general, the vertex form is equal to a times x minus h squared plus k. And we said in class that the h value, the horizontal component of our vertex, is always the opposite of what we might expect because of this negative sign. So since our vertex was 4 units to the right of the origin, we're using a -4 here. Since our k value was 4 units below the origin, we are using a -4 here, as we would expect. So that's our vertex, and then our a value gets placed here. So that's our vertex form. No problems there. Well, hopefully there were no problems there. But what about the standard form? Well, the standard form requires just a little bit of work. We haven't talked about this in class yet, but we'll demonstrate it now. The standard form does take a little bit of algebra, and what I'd like to remind you of is that this x minus 4 that's being squared right now could be written twice. We could write x minus 4 times x minus 4. And my screen just went blank. I don't know if that happened on your end or not. Okay, I think we're back. Let's see if we've got it now. All right, so we said that we could, here we go, we could write our x minus 4 twice. That's what it means to square a number, so we just wrote it twice here. Now, let's just FOIL that together, because we know how to do that. And I would challenge you to try to FOIL this in one step using mental math. We recognize that the x will multiply by the x and give us an x squared. We also recognize that this x will multiply by -4, and the middle term, -4 times x, will also happen, and those two are the same result, -4x and another -4x, and they will combine, since they are like terms, to -8x. And then finally, -4 times -4 for these last values in this position. -4 times -4 is positive 16. So now we've got this expression FOILed. We can go ahead and distribute this -2 back into the group. -2x squared positive 16x negative 32. And we still have this -4 that's hanging out on the backside. And now -2x squared plus 16x minus 36 appears to be the appropriate standard form equation after we combine all of our like terms. So as we had mentioned yesterday in class, I think it's very easy to work with vertex form, but unfortunately not all of our equations will be presented in vertex form. So if we can spot what the vertex form of the equation is based on the graph, then with 2 or 3 steps, we can then generate the standard form as well. And now we can work with either form as needed. Let's try another example. In this case, we have a vertex that's located at -4, +3, -4, +3. And the a value, well, let's see, if I look at my scale, I've got to be careful here. It actually takes 2 grid lines for me to move over 1 step. So if I step to the right 1 unit, I do go up 1 unit. So that tells me that my a value is 1. While we're here, let me look at this guy. If I would step over 1 unit, I would have to drop down 2 units. So that tells me that this one has an a value of -2. So hopefully that makes a little bit more sense. I know there were some questions on that yesterday, but that's all that I'm looking at for our key data points here to establish the a value. So now that we have our a value and vertex, we can write our vertex form of this function. And that vertex form is simply f of x equals 1 times x plus 4 squared plus 3. A value of 1, h value of -4, which makes this a plus 4 on the inside because we have to write the opposite of that, and then a k value of 3. That's our vertex form. That's the first part of our answer. Now we need to expand it to get our standard form, the second part of our answer. Now this a value of 1, that's not going to affect our distribution whatsoever, so we can pretend that it's not there anymore. And simply consider x plus 4 times x plus 4 plus 3. And x plus 4 times x plus 4 when FOILed will turn out to be x squared plus 8x plus 16. And if you start to notice a pattern how this trinomial looks compared to the squared binomial that we have back here, then that would be great to utilize the shortcut that you observe. Just be very careful that you utilize it correctly. Now in this last case, we'll combine like terms, and it appears that 16 and 3 are the only like terms. So we'll combine that to make x squared plus 8x plus 19, and that's our standard form. Let's go through another one. Our vertex is located at -2, 3. Our a value is equal to 3. Now this image may be a little bit blurry here, but I did have to step to the right 1 unit and up 3 units to reconnect with the graph. So therefore our vertex form of the equation is 3 times the quantity of x plus 2 squared plus 3. And I've expanded the binomial squared by recognizing the shortcut here for the standard form. There's step 1. Step 2 could be to distribute in the number 3. That was that leading coefficient. And step 4 is to combine any other like terms. So now we have a standard form of the quadratic function and a vertex form of the quadratic function. Let's try one more. Our vertex is located at 4, -1. Our a value, now I'm moving 2 grid lines to the right, but that's because 2 grid lines are necessary to show 1 full step to the right. If I move to the right 1 full step, I only drop down half of a step. Notice the scaling here. I'm only going to the right 1, but down a half. So that tells me that my a value is -1/2. Negative because we had to step down, and 1/2 because we only moved 1/2 of a unit. So I think it's safe to say that our vertex form is f of x equals -1/2 times x minus 4 quantity squared minus 1. Again, we're using a -4 here because we are shifting to the right, and it may be the opposite of what you'd expect, but that's correct. And we're using the -1 because we did shift down. So let's see if we can expand that for our standard form. So here again, I used the shortcut. If you haven't picked it out yet, we square this number to record our final position in that trinomial, and we double that number to locate our value here in the middle. It always works that way when we FOIL properly. Then we can distribute the -1/2 into each of these 3 terms. Remember, it only goes to the terms that are connected with the parentheses here. It does not extend to the -1 at the end. And then we can combine our like terms, the -8 and the -1, in the final position. And we now have our standard form and vertex form of the quadratic function that represents this graph. So again, I hope that helps. Let's move on to a couple other examples. We can now generate equations based on the graph. Now we're going to analyze the behavior of the function again by looking at just the equations. Now, I don't think I'm actually going to do any of these examples in this video, but I left this question here because the phrase extreme values. We hear that a lot in pre-calculus and then ultimately in calculus as well, so I wanted to introduce it to you now as an Algebra 2 student. The word extreme value in this case generally means a maximum or minimum point. So it's not extreme that it's, wild and crazy and weird or anything like that, but extreme means the highest point of a graph or the lowest point of a graph. And so if you think of it that way, then it might also resonate with you that the extreme value of a parabola is always going to be its vertex. So essentially this question is asking you, can you identify the vertex from these equations? And once you find the vertex, can you tell me if that vertex is going to be at a maximum or a minimum? So we'll do that, not at this point in the video, but in the next series of questions here. Again, this is just a little bit of a vocabulary word that I wanted to share with you. And I think I made a mistake with my instructions here. I meant to include an extra piece of the instructions here, so I'll go ahead and add it. We are going to identify the x and y intercepts with these equations and the extreme values. Sorry, that piece of instruction should have been in here. So we'll find all three in these examples down below. And since we're going to find all three of these components, it would be nice to have just a small set of rules to work by. So these are the rules that we're going to reference to find all three of those components. Number one, when finding an x-intercept, you always set f of x equal to 0 and solve. For number two, to find a y-intercept, we always set x equal to 0 and simplify. And then finally, for our vertex, we talked about this in class earlier this week, the coordinate for the vertex is the opposite of b divided by 2a, the x coordinate is the opposite of b divided by 2a, and the y coordinate is the function evaluated at that result. So we'll get some practice with that now. So make sure that you have these three rules written down or at least memorized, and we shouldn't have too much trouble simplifying these examples. So let's go take a look. Okay, so to find our x-intercepts, we have to see where this graph touches or crosses the x-axis, and we'll do that by setting the entire equation equal to 0. And this should look familiar to you, negative 2x squared minus 12x minus 19 equals 0. These are the types of equations we were dealing with last week. Now, keep in mind that we could use the quadratic formula or a factoring method to solve this, but I do want to point something out here. The discriminant calculation from last week will tell us how many solutions there are to this equation. And remember, the solutions in this case are going to be x-intercepts. So before we even use the quadratic formula, if we're so inclined to use that, let's calculate the discriminant first and decide how many solutions we should see. Then we can go to our calculator and utilize it if you're not factoring. So we have negative 12 for our b value, and we have a negative 2 for our a value, and negative 19 for our c value. And I calculated this off screen because the calculator is not running properly on my computer right now. But this came out to be a negative 8. Our discriminant is negative 8, so therefore there are no real solutions. And what that means for us today is that there are no x-intercepts. So as far as part number one here, this graph, downward facing parabola, evidently will not touch or cross the x-axis. So that's good to know. Okay, so when being asked to identify the x-intercepts, we can, without even looking at a picture, say that there are no x-intercepts. All right, part number two, what about the y-intercepts? Well, that's actually pretty easy because we know that our c value, based on prior discussion, is the y-intercept. We also know that we could simply substitute 0 in place of x, but if you substitute a 0 in place of x, don't you notice that negative 2 times 0 squared and negative 12 times 0, both of these terms essentially disappear, and we're left with the c value anyway. So our y-intercept is simply 0, negative 19. That's the coordinate of our y-intercept. And lastly, and I didn't quite give myself enough room here, to find the vertex, we know that we'll use the opposite of b divided by 2a to establish our x-coordinate of the vertex. And then we'll use that x-coordinate inside the function to evaluate our y-intercept. So I'm going to just slide over here. I'm sorry, not y-intercept, but our y-coordinate of the vertex. So we'll slide over here and calculate our vertex. The opposite of b divided by 2a would be the opposite of negative 12 divided by 2 times negative 2. You could use a calculator if you need to, but I think we can do this mentally. So we now have positive 12 divided by negative 4, which comes out to be negative 3. So we now know that our vertex is located at negative 3 on the x-coordinate. And we can use this negative 3 inside the function. So we have negative 2 times negative 3 squared minus 12 times negative 3 minus 19. I'm just using the original function and substituting the number negative 3 into it. So negative 3 squared is 9. 9 times negative 2 is negative 18. Then we have negative 12 times negative 3. That becomes a positive 36. There's that combination that we've seen many times already. And negative 18 plus 36 is positive 18. Positive 18 minus 19 equals negative 1. So we now know that our y-coordinate of the vertex is located at negative 1. And there we have it. We have no x-intercepts on this graph. We do have a y-intercept at 0, negative 19, and we have a vertex at negative 3, comma, negative 1. We could go to a graph at this point and recreate it. In fact, many of you would probably graph this using Vertex Form. It's actually left 3 and down 1 for a vertex, and since our a value is negative 2, I know that it's going to be a parabola that's taller than usual and pointing downward, and evidently it will strike the y-axis at negative 19. So all of those characteristics seem to hold true here. If I were to plot this accurately on a on a piece of graph paper, this is what we would see. Let's try another example. This one might be a little bit more manageable. In step 1, we want to find our x-intercept, so that means set the equation equal to 0 and solve. This doesn't look factorable to me, so I'm not going to bother with that, so I'll go through the quadratic formula. First, I want to verify the discriminant. In this case, we have negative 4 squared minus 4 times negative 1 times negative 2. So this one looks like 16, and then negative 4 times negative 1 is positive 4 times a negative 2 is negative 8. So 16 minus 8 looks like our discriminant is equal to 8. So that tells me that there are two real number solutions to this, and we could go ahead and find them using the quadratic formula. So if we reach for our calculator and use the quadratic formula plus program and the quadratic formula minus program, we should be able to establish a result. Now remember, on those programs we do have to supply an a value, a b value, and a c value for each. And since we are all using the TI Inspires, we can just simply report the results here. Now those that are simplifying by hand, or those that are looking for a challenge, we could substitute into the quadratic formula and end up with 4 plus the square root of 8 divided by 2 times a, which is just 2, or 4 minus the square root of 8 divided by 2. And when simplified, let's see, we can actually simplify the square root of 8 to 2 square root of 2. Right, if we did our factor tree off to the side, or if you've seen this one enough now, you could probably handle that in your head. 4 plus 2 radical 2 over 2. And then lastly, these three coefficients have a factor of 2 in common. So within each of those examples, we can actually factor a 2 and simplify this finally to 2 plus the square root of 2 and 2 minus the square root of 2. We haven't done that much in class, so we'll talk about this one tomorrow. But I do recognize that a lot of you are using the quadratic formula program that we built, but it's on a non-CAS calculator. So there is a distinct possibility that your calculator is simply returning decimals to you, which is perfectly fine. Oops, and I just realized that this was actually a -2. 2 times -1, -2, -2. So if we were to simplify that, well, we would end up with the same pair of results, but I think our signs would be different. I think we'd have a minus here and a plus here and a minus here. But the two final answers are exactly the same. No changes there. But anyway, back to the calculator. If we use the plus sign, then I think we would end up with, shoot, I missed this too. Then dividing by that -2 would have produced this result. Yeah, -2 minus the square root of 2 and -2 plus the square root of 2. Okay, that's better. Okay, so our decimal values as a result would have been -0.5858 when rounded. I'm looking off screen because I have my calculator over there. And then this answer, when using the subtraction sign, the plus sign in the quadratic formula, ends up being a subtraction sign here. We end up with -3.4142. So I prefer to see 4 decimal places as the solution, and we can obtain that again by using the quadratic formula. I'm going to delete this problem and get it out of the way so that we can complete step number 2. This is the easy one. How do I find the y-intercept? Well, I set x equal to 0, or I recognize that the y-intercept is located at this c value. Now I'm going to report that as a coordinate rather than just a number. So we now have y-intercepts here and x-intercepts here. I should probably report that as a coordinate too. These are technically better answers because they are reported as a coordinate, and intercept is a coordinate, not just a number. Okay, so we have our x-intercepts, we have our y-intercepts, and now finally our vertex. Well, again, our vertex was found by using this mini formula, opposite of b divided by 2a. Take that result and substitute it back into the equation, opposite of b divided by 2a into the function. So our opposite of b ends up being +4, and 2 times -1 is -2. So we can make that substitution. 4 divided by -2 is pretty straightforward, -2. We'll take that and plug it into the original formula. So we now have -2 squared minus 4 times -2 minus 2. And then simplify. Well, this 4 squared becomes -4. This -4 times -2 becomes +8. And then we have a -2 at the end. So it looks to me like our vertex is at -2. 4 minus 2 is +2. And we've got our key components necessary to create this graph. So this video is getting a little bit lengthy, and I'm certain that the first few components of the video should go very well for you. We've spent a fair amount of time discussing graphs of quadratics and now equations of the quadratics, so I certainly expect the first half to go well. Please make sure that you revisit those and understand them. For the second half, I know that some of the calculations got to be a little bit more aggressive than we're used to seeing, but this is the direction that we're going with class. So if you were struggling with the second half of the video here, I understand. We'll have some more time to work through them and talk through them tomorrow. But please do copy these examples, work through them, maybe try 1 or 2 more on your own, and then send me what you get by the end of the day today. Thanks for watching.